Spatial. This is Patrick O'Shaughnessy, and I will be discussing spatial graphing techniques in this module associated with the InTERACCT series. In the second part of the module, we will now discuss the details of graphing spatially derived data, with the objectives of understanding the concept of measurement interpolation and steps for plotting a spatial map in Excel. Now, a concentration value is required at each grid node in order to develop a contour plot. However, typically there will be many more grid nodes than sampling locations. Therefore, an interpolation method is needed to estimate a concentration at each node. As you can see here, the concentration applied to a grid node will be computed from concentrations measured at nearby sampling locations. Here, 6 samples nearest to a particular grid node are used to determine the concentration at that node through an interpolation technique that includes all 6 sample concentrations. The mathematics of the interpolation process can also apply a weighting factor to account for the distance from the measurement location to the node, so that locations further from the node have less influence than a measurement near the node. The process is then repeated for the next node and every other node to provide an interpolated concentration at each node needed to then create a spatial map of the area. It can be seen here that the more measurements, the better the estimate of concentration at each node. The 2 spatial graphs shown here were developed by Kohler et al., who were comparing the outputs from 2 different interpolation methods. One is the inverse distance weighting method, in which the concentration at a sample site is weighted inversely to its proximity to a node to increase the influence of nearby sampling locations. The other method is called kriging, which uses exponential relationships to weight sample concentrations. In both methods, samples collected closest to a grid node have the greatest influence on the interpolated concentrations at that node. Of the different software types shown, obviously Excel would be the most easily available and usable of the types of software that can develop a contour plot. But Excel does not have predefined functions to perform spatial interpolations. R is a freely available statistical software package that has predefined functions such as IDW for inverse distance weighting. The R functions interp2 and gstat create very nice contour plots and implement the interpolation routines needed. More specialized software such as Surfer and MATLAB can also be utilized, but there's obviously a cost and a steeper learning curve involved. So to provide more information on Excel, again, a spatial interpolation routine would be difficult to set up from scratch. However, vendor-supplied add-ins can be purchased to perform spatial interpolation. For example, the company ExcelWorks provides a set of add-ins referred to as Excel Lab, within which is the function interpxyz that can compute the interpolations needed at each node. Likewise, vendor-supplied add-ins have been created to enhance contour plotting capability of Excel, as shown in the list here, such as Chart Studio, Office Expander, Origin Lab, and dplot. So here's a rudimentary example of creating a contour plot in Excel that can be applied to spatial mapping. Let's assume the space given in the previous example is 32 feet by 28 feet, so that each node is 4 feet apart. The 6 sample locations in the room are given in the table, assuming bottom left is 0, 0. A mobile sampling device was then placed at each sampling location, which provided measurements of an aerosol between 3.5 and 8 milligrams per meter cubed, as shown in the table and in the floor map. An interpolated concentration value is then needed at each of the 9 times 8, which equals 72 nodes of the grid map. The ExcelWorks interpxyz function was then used to determine those interpolated concentrations at each node. The resulting values are shown in the truncated table. To obtain a contour plot of the concentration plot profile over the plant floor, the interpolated values need to be put into table format as shown here. The rows represent the north-south locations and the columns represent the corresponding east-west locations. Applying a contour plot in Excel is relatively straightforward, but some not so obvious formatting changes are needed to enhance its appearance. First, the table values and the associated row and column distance values need to all be highlighted. Then choose Insert, select Charts using the little down arrow to open all possible chart options, then choose Surface, and then choose 3D Surface as shown in the image of the final drop-down here. And yes, we need to create a 3D surface plot first. And here is the result from the first output from Excel. In that display mode, the Z-axis can be chosen, which gives us options as to how many quote-unquote elevations of concentrations or bins are provided, as well as their overall range. So click on the Z-axis and choose Format Axis, and then Axis Options as shown in this drop-down. And the minimum and maximum of the bounds can be set, for starters, and then the major unit then sets how discretely the map is split up into color zones. The default here is every 2 units, but it was changed to every 1 to double the number of color bands. So now the 3D plot has more color bands as shown here. With those changes made to the Z-axis, the chart type can be now changed to contour, and here the title is also deleted. The color scheme can be changed from this default of multiple colors of certain shades to other multiple color shade patterns, or even to monochromatic shades. These are more typical when displaying a spatial map and are often referred to as heat maps. To make those changes, click on the plot first, which will show chart design in the ribbon above. Then click on that to show a bar of options including change colors. Clicking on that brings up the color patterns available, and you can see the red monochromatic pattern was chosen. The result is shown here. Notice, however, that the colors have kind of a gray tint to them. This is helpful for giving the illusion of kind of like mountain-like contours. But here we just want to emphasize one bin from another. So to remove the shading, we need to click on the legend below the plot, and then click again on a single bin indicator, which will bring up this Format Band drop-down. Once in there, the 3D format options are found, and then the Material option is clicked. The option in the standard selection needs to be changed to the third one in the Special Effect category, which is labeled Flat. You can't see it here, but that's its label. Unfortunately, this needs to be done for every bin as well. Here is the resulting contour plot as a heat map of concentrations over the measured and interpolated floor space. It obviously shows a gradation from low concentration in the lower left to highest concentration in the upper right. The study by Liu and Hammond provides an example of the use of Excel to create the contour plot of exposure concentrations as part of a spatial mapping effort. This schematic of the plant floor shows both the stationary monitors, identified near columns in the plant that were labeled as P with some number or M as some number, and the aerosol monitors as circles with X's through them, and that were fairly coarsely spread throughout the plant. The nodes of the grid can also be seen faintly in the background. Here is the contour plot created in Excel by the authors. As can be seen, it uses the default color scheme, and there are some high concentration areas around spots where measurements were made. However, given the fairly wide-spaced locations of the sampling spots, and because of the need to interpolate a lot of grid nodes between those locations, the concentration contours are relatively unrefined between sampling locations. More effort to obtain more actual measurements would have helped to get a better sense of the concentrations throughout this plant floor.
This lesson has been created by the Interdisciplinary Training, Education, and Research Activities for Assessing and Controlling Contaminants from Emerging Technologies Program, a collaboration of the University of Minnesota School of Public Health, the University of Iowa College of Public Health, and the University of California, Los Angeles Fielding School of Public Health. Funding for InTERACCT is provided by the National Institute of Environmental Health Sciences of the National Institutes of Health. The content of this lesson is the sole responsibility of the developers and does not necessarily represent the official views of the National Institutes of Health.